In this problem, a particle is moving at a constant speed along a line from the point P, which is 2, -1,5, to the point Q, 5, 3, -1. We want the parametric equations between the line, assuming it takes 5 seconds to get from P to Q. So in the first rundown of this problem, let's assume at time 0 we're at P, and at time 5 we're at Q. Because this makes our problem fairly simple. Because what's going to happen is we're going to start at P, and then we need to figure out what direction we need to move in each axis, the X, Y, and Z, to get to Q. Well, one nice way of representing that is finding the vector between them. Let's call it PQ. That's the vector from P to Q. So 5 minus 2, we're just subtracting their corresponding pieces. 3 minus -1. And then finally we have -1 minus 5. And what that does is that gives us the direction we need to go to get from P to Q. So we have 3, 4, -6. Now, the next thing we need to do is, now that we have the direction we need to go, we need to figure out where we were starting at. So as a vector valued function, let's call it r of t, we're starting at P, so 2, -1, 5, and then I'm going to be adding a multiple of 3, 4, -6. Now, there's going to be a variable in here because this is now going to be a function of t, but we can't just put in t because that would still work for time 0. The problem is at time 5, if I put in t, we'll now move in 15 units in the x direction. So that would put me at 17 for an x coordinate. So we need to divide t by something. Well, let's divide it by our change in time, which is 5. So we can do t over 5 here, and now we see if we put in 5 over 5 is 1, so that's going to move us exactly 3 in the x direction, 4 in the y, and -6 in the z, which will get us at point Q at time 5. So x of t is 2 plus 3t over 5, or 3/5 t. Y of t equals -1 plus 4t over 5, and z of t equals 5 minus 6t over 5 would be our parametric equations. And you should always give an interval for your t with parametric equations. For this one, t is going to be in between 0 and 5. Okay, we're going to leverage what we've just done, and let's say we were told that at point P we're at t equals 1. Well, that would mean if we're going for 5 seconds to get to Q, that means it's going to be t equals 6 at Q. So let's think about what's the same and what would be different. Clearly our starting position is now different. But our points are the same, our vector PQ would be the same, and our change in time would be the same. So I'm going to show you a nice quick way to handle this so that we don't have to redo everything. And basically what we're going to do is we're going to shift the time. So instead of me putting t in here, I'm going to put in t minus 1. So when I calculate that r of t, which we had the vector 2 minus 1, 5. Again, ranked in this is a vector valued function. Instead of putting t here, I'm going to put t minus 1. Probably don't need parentheses there, but it's not going to make it wrong to put them in. Everything else stays the same. This is a neat little way of handling parametric equations if we change the starting time. Because look at what happens now. If I put in 1, this becomes 0. 0's at this part, and heck, I'm at point P. If I put in 6, 6 minus 1 is 5. 5 over 5 is 1. And that adds our direction in the x, y, and z directions. That adds our distances in the x, y, and z directions to land us at point Q. And then once again we could write this out as our x of t, y of t, z of t that are over here, except we'd have the t minus 1s. And our t range would be from 1 to 6.